Today we're very happy to have our invited speaker, Professor Mathieu Barthélémy from Universite Grenoble Alpes in France. And so Mathieu has been working for the past several years on building, I believe, the first university space center at University of Grenoble. And he's here to share with us his experiences on that, as well as some of the missions that they've been working on. Mathieu, please feel free to go ahead.
Thank you, Roland. Yes, in Grenoble, we built a university space center, as you mentioned, and dedicated to space instrumentation and space data exploitation. And during this talk, we try to explain you what kind of measurement you can do with cubesats for space weather and especially for auroral monitoring. And I will specifically talk about two missions that we are developing in Grenoble. So one is AMCA Set, already launched in September last year. Another one is ATIS, and I will say a few words about the other project at the end of my presentation. So the topic is really to talk about space weather, and space weather, which is let's say the science of the interaction between the sun and the Earth. There is a European definition saying that it is a, let's say, physical and phenomenological state of natural space environment. And I like that it needs some observation and monitoring, both of them. So for this, it is very important to have some, of course, ground-based instruments. But as you know, ground-based instrument can be affected by, let's say, the clouds when it's optic measurements or some other problems. So it is very interesting to observe from space space weather phenomena. And we can say that there are two ways to work. One is to find some new observable quantities, meaning new instruments that can be miniaturized to fit in CubeSats. And the other one is to try to do some large-scale monitoring, if possible, with constellation. And for this, CubeSats are really, really interesting because you can develop some constellation, let's say, at reasonable cost. So for this, really, space weather is a critical application, let's say, application way of the CubeSat. Of course, there are a lot of CubeSat projects with space weather payload. In 2017, for example, there was in Washington, D.C., in the USA, a meeting. I copied the link where you can find the presentation of this meeting, with a lot of proposed projects for space weather. What can be seen from this this project, and of course of the project from between 2017 and now, is that they are mainly dedicated to LEO observation, meaning low Earth orbit. It is logical because CubeSat, the first CubeSat did not have some propulsions. And then for regulation question, you only can reach LEO orbits. Now, propulsion, miniaturized propulsion exists, and we can hope to go, let's say, at higher altitude orbits, or let's say outside the very close Earth environment. And that is very important for space weather, and CubeSat can play really a role, very interesting role. Then what can we do with this CubeSat? Of course, the easier is to think about plasma monitoring, so it can be particle spectrometer, long-beam probe, for example. You also can monitor the neutral atmosphere, especially the oxygen density, which is critical for the drag of the satellite, and which is one of the critical parameters for space weather. You can also monitor the wave, for example, the ULF wave in the ionosphere, and you can do some optical measurement, especially monitor the aurora or the airglow. all this monitoring means some specific instrument. And for example, for auroral monitoring, you can have some imagers or spectrometer. So I will talk with this let's say optical measurement, which can be very, very useful for space weather and can fit with cubesats. So I will give two examples we are developing in Grenoble. AMCA Set launched last year, and ATIS, which is planned to be launched in 2023. On the right, you can see one picture taken by AMCA Set, and I will talk about some, let's say, of the defaults of the image. You can see some dots, which are some defaults in the radio transmission, and that could be critical. But first, I will give some, let's say, scientific highlights of why it's important to monitor the aurora for space weather. So the main question we address is, what are the particle fluxes at the top of the atmosphere? Of course, these fluxes are very important. They can damage the satellite. They can produce some ground-induced current, which can damage the electrical network. So all of these fluxes are important. And of course, these fluxes are depositing their energy into the atmosphere and can create some perturbation. For the aurora, the energy range that are concerned by this particle are the EV and KV range, let's say up to 50 keV, a bit higher. So it means that this is particle coming from the plasma sheet in the magnetosphere, where the particles are accelerated. And they deposit their energy, let's say, between 90 and 300 kilometers. But they can cross the trajectories of, let's say, satellites, especially in low Earth orbit. And then they can create some surface charging on the satellite surface and create some discharge. And often this discharge can damage, let's say, the solar panels especially. They also can create some ground-induced current. And you know that there was, in 1989 in Quebec, in Canada, a disruption due to this ground-induced current. So this is very important. Scientifically, we can also track the overall extension, and that gives us some information about the processes in the magnetosphere. We can have an idea of the auroral overall extension, and can also have some small-scale structure. So we can say that the aurora are tracer of the magnetospheric processes, and it's for this very important to monitor them. So we choose to do this monitoring with two CubeSats in the Grenoble University Space Center. So let's say, what are the scientific objectives of both ATIS and AMCA Set? One very important point is that this altitude region, let's say typically between 100 and 400 kilometers, is very difficult to reach. Some of our colleagues in France call it the ignorosphere, meaning that it's very difficult to have information about that. Why? Because it's too high for balloon in situ measurement. You cannot reach altitude higher than 50 kilometers. And it's a bit too low for in situ measurement of satellite. So you need remote sensing, and aurora are a very good way to do some remote sensing. So let's say that when you are doing this remote sensing, you can do, of course, some imagery of the aurora and take some information about the shape, the color of the aurora. You can do some full spectrum in the UV or in the visible, and that is also very interesting. And the best is, of course, to do some spectroimagery, but it needs a bit larger instrument. But you will see that we are trying to make some effort to miniaturize this instrument. Of course, we need some monitoring. So it means that we need some long-term continuous observation. So from the ground, you have problems with the cloud coverage. And of course, more than the half of the time, you have some daylight, and you cannot observe the aurora. So observation from space is very interesting in this sense. So what kind of observation you can do from space with a satellite, especially a CubeSat? You can do some nadir observation to map the aurora. Of course, you can have some difficulties. The reflection of the moon on the clouds or on the ice sheet or snow can perturb the imagery. But you can reconstruct the map of the aurora with quite wide field imager. So I put two pictures of AMCA Set, one where the aurora was quite fully green and one where there was some red and some different colors. Then when you are aiming at the nadir, you can have a column integrated intensity. And if you look at the at this column integrated intensity, versus the mean energy of the particle fluxes, you can see that it varies, and each line have its own variation. So dealing with, let's say, the ratio of each line, you can reconstruct this mean energy of the particle. What is also interesting is that with the total flux, it's almost linear. So mixing the total intensity and the ratio of the different line, you can reach both the total flux of the, especially of the electron, but also of the protons, and the particle energy, mean energy, meaning that you can characterize the input into the atmosphere. So that is very interesting. Then you can also observe from the limb, and that's also at the limb, and that's also very, very interesting, because you can reach the vertical profile. And it is very interesting because each emission line has its own vertical profile. And it's very interesting to fit this vertical profile and give you much more information. Another very interesting point is that when you are observing at the limb, you can observe on the day side, and it allows you to reach some day side aurora, which can be also very interesting. You know that there are some specific input into the atmosphere, into the magnetosphere, when the solar wind has particular configuration, especially when the magnetic field of the solar wind is directed to the south. So there is a strong interest to observe both at the limb and at the nadir. So we are building two satellites for this survey. So AMCA Set, you can see on the picture the AMCA Set just before the integration on the pod. So it's a 2U satellite with an imager, a wide field imager. The diagonal is 42 degrees, and it has been launched on a Vega flight from Kourou last September. And we are also developing ATIS. ATIS is a spectrometer and a particle detector to monitor the electron up to 30 keV. And we are trying to launch it, and the plan is to launch it in 2023. We are a bit late regarding our initial plan, but we will launch it within 2 years. Then AMCA Set, so you can follow AMCA Set. The NORAD ID of AMCA Set is 46287, and you can follow it on the SatNogs, meaning the radio amateur website. You can have all the telemetry of AMCA Set, so that's very interesting. AMCA Set is on a SSO, slightly elliptical, between 530 and 540 kilometers. What is pity is that since 10 days after the launch, we experienced an ADCS failure, meaning that we cannot orient the satellite. This is a problem with the microcontroller which control the ADCS, which got a latch up and crashed. And so hopefully it is still rotating a bit, and we can take some picture, but we have to wait the good position to before doing some picture. We submitted a paper in GMAS recently in March. We are waiting for the report of the referee on how we can process the AMCA Set images. It is particular images since it is a sparse RGB detector, meaning that only 1 pixel over 16 is colored, and the other ones are black and white. So the payload of this satellite is an imager. So the imager is based on a commercial detector from Teledyne E2V, named the Onyx. It's a detector with large pixel, 10 micrometers, because we need some flux and we need some height sensitivity. It's a 1.3 megapixel. Then we designed a specific objective with a focal length of 23 millimeter and an aperture, quite large aperture, f over 1.4. And this is this objective that we sent in this 2U satellite. So you can see a picture on the right, a real picture of the objective, and the draw of this instrument. We also did design a baffle to allow to take some picture on the day side at the limb. Then, of course, if you want to interpret in terms of both mean energy and total flux of the electron, you need an absolute photometric calibration. And as you probably know, the instrument can experience a degradation in its sensitivity during the flight. So we need to recalibrate regularly the instrument. The idea is to aim the moon, and because the moon is one extended source which is photometrically very, very stable. The variation is less than 10.8 by year, so it's very stable. Of course, you have a cycle with the moon phase, but it's very stable. And you can calibrate imager and spectrometers using some code developed by the CNES in France, and they are named Rollo and Polo. And you can reach an accuracy between 2 and 5% in absolute photometry and 1% in relative variation. So it's very interesting because, in fact, you can have a quite high accuracy calibration of your instrument with this, and you can follow the sensitivity of your instrument during the flight. Then we developed an imager and a spectrometer. What are the advantages of an imager and a spectrometer? Of course, an imager, you have a wide field, so you can see the structure of the aurora on a quite large part of the field of view. But of course, you can be perturbed with the moon. And you only have, let's say, 4 channels, one RGB channels and potentially one black and white channel. It means that the color information is quite reduced. With a spectrometer, you can have all the lines emitted by the aurora, and then you can have some more information. But it is much more difficult to do a wide field spectrometer. So ATIS is a narrow field spectrometer with, let's say, each field with each field of view getting 1 by 1 degree of aperture of field of view. But you can have all the visible lines with a medium resolution, let's say around 1 nanometer. And the specificity of this spectrometer is its very, very high sensitivity. You can detect a line within 1 second exposure time if its intensity is a bit more than 5 Rayleigh. So you can have some very, very faint line, and that is very interesting because you increase the amount of information you get from the aurora, and of course you increase the sensitivity and the precision of your flux reconstruction. Then ATIS will be launched in 2023 for a 2-year nominal mission, if possible extendable to 5 years. And we are thinking of what is the best orbit for this. For let's say auroral monitoring, could be very, very interesting to have a shift in local hour because in this case, you can explore all the physics at different local hour in the magnetosphere. But it's very difficult to obtain such a launch. Main part of the launch are at low inclination orbit or on SSO. So we also accept SSO orbit, despite the fact that the best orbital choice is between 70 and 80 degrees of inclination. We will have 6 lines of sight distributed along the vertical, allowing to reconstruct the vertical profile of the aurora between 100 and 350 kilometers. And we aim 1 second exposure time for this instrument. We also aim to do some measurement in the aglo, but of course the intensity is much lower. And we think that it could be possible to reach some information on the aglo within 20-second exposure time. We did a ground-based demonstration in March 2017 in Norway, and you can see on the graph here 1 night of observation. So on the left you have 8 hour local hour, and the morning on the right, and you have more than 80,000 spectra on this graph. You can see the green line in the middle and the red line above, some nitrogen line at longer wavelengths, and the 427 nitrogen ion line here, if you can see my mouth. So there is a lot of information in this spec, but on the first version that we run in 2017, we still have some problem in the line intensity conservation, and of course it makes the data processing much more difficult. So we fixed this problem since. You can see this instrument. So it's a piezo interferometer, and you can have here the optical path here, and the piezo is directly glued on the entry lens. Then you have the detector. In fact, you have 3 detectors vertically disposed, and each line of sight is reaching 1/2 detector. This is why you have such a disposition. Then, of course, it is quite a large instrument, so it will fit with a 12U satellite, and we are developing this satellite with the Montpellier Space Center, and they are building the platform, and we are building the payload. That's very interesting collaboration, and we specialize our space center, Grenoble more on payload and Montpellier more on platforms. So, of course, with only the spectrometer, it's quite difficult to interpret the data. So we add the same imager as AMCA Set on the ATIS mission with this wide field of view. And the idea is that we will see the aurora, as you can see on the image on the right, and you will see the 6 line of sight, the integration. So, for example, the last one on this picture is on the cloud, but this is for an example, but is not in the aurora. So you won't have any signal, but the second one will have some signal, etc., etc. So it's very important to interpret the data, and it's also very important to cross-check the total intensity, seeing if one of the calibration can have some problem, or if one of the instruments has a degradation of its sensitivity. So it's very important to cross-check this. It is scheduled. It is in phase B, and it is scheduled for mid-2023. We do not know still what will be the rocket. So then, to interpret this information, we use a kinetic code named transsolo, calculating the solving the Boltzmann equation into the along a vertical or along a magnetic field line into the atmosphere. So it takes as input the precipitating electron, and on the day side the EUV solar flux, and you have as an output the thermospheric emission. And of course, we are trying to test some inversion method of this code to reconstruct the precipitation of the electron. We fit two main parameters, so the total energy and the mean energy of the distribution. We are trying to see if we are able to fit some additional information, for example, the width of each distribution. But at this stage with AMCA Set, we only fit these two parameters, total energy and mean energy. Then this is the first interpretation we did on AMCA Set. So AMCA Set, as you know, this is a detector, a spare CGB detector. Then we took the sensitivity of each detector. We took a part of the image. So we did a first set on this part, of this blue part of the image, and we reconstruct the line, the main line intensity, meaning the green line, the red line, the blue line, and the 427 line. Of course, it does not mean that the green line is only the green channel intensity, because if it's, of course, a majority, you have some parasitic light that can come, and you need to correct from this. This is why you have such complicated matrix inversion to do for this reconstruction. So we submitted this paper in GMAS, and we are waiting, but we were able to reconstruct the mean energy. So on this aurora, we had a mean energy of 3.02 keV and a total flux of 5 erg, around a bit more than 5 erg per square centimeter per second, which is a quite typical aurora, not too bright, but a quite typical aurora. Of course, we also performed some observation at the limb with AMCA Set. So you can see here, it's a very interesting picture of AMCA Set, because you have here the terrestrial globe, you have here the limb of the Earth, and what is interesting is that you can see both an aurora at the limb and a part of the aurora at the pseudo nadir. To check that it is the limb, we trace the profile of the intensity on the red line here, and you can see on the right the curve of this profile, and it definitely corresponds to an altitude profile of the intensity line. Of course, this is an arbitrary unit, and there are still some bias, but it's very interesting to see that it definitely corresponds with a quite sharp decrease at low altitude and less rapid decrease at high altitude. So this is very interesting, because with this image of AMCA Set, we have a picture of the aurora at the limb. Of course, you can see these black dots. This is failure in the radio transmission, and you can also see them on the curve. This is the point which is lower of the main curve, because of course, when you integrate on 10 by 10 blocks of pixel, if you have several black dots, you cannot see, you have a lower intensity. But the main, let's say, the main shape of the curve is regular, and we will correct from these black dots in the future. For the spectrometer, of course, the idea is to minimize the intensity of each line in different geometry with the transolo output. So you have a test here on the new version of the AT spectrometer on a laboratory lamp. So it's a mercury argon lamp, and you can see that we can reconstruct a lot of line, and we are able to to reconstruct the intensity. Now we solve the problem of the line intensity conservation with this instrument. We will perform a next campaign from the ground with an engineering model of ATIS in November. In fact, it was planned in March this year, but due to the COVID crisis, it was impossible to travel to Norway without very, very complicated restrictions. So we canceled the campaign. So what are the conclusion and the take-home message for this? We developed two different instruments for space weather monitoring. One with especially for low energy electron. One imager with a calibrated space RGB images, both at nadir and LIM. One spectrometer with 6 vertical calibrated high sensitivity spectra each second. So with only 1 second exposure time. So that's very, very short. Of course, the idea is to have a quite precise monitoring of the particle precipitation and energy deposition. And that is very important for space weather monitoring and also for the physics of both the ionosphere and the magnetosphere. And that can be done with 2 CubeSats, one 2U and one 12U. So it's important to keep in mind that we can do some optical measurement with CubeSat, quite precise optical measurement, but more wider. There are very, very, very large potentiality of CubeSat for space weather monitoring. Definitely, it is a very, very interesting tool for space weather monitoring with a very wide panel of possible instruments, particle detector, land with probe, and also some optic instrument, which is not immediately in our mind because we often think that optic instruments are quite big and cannot fit, but they can, and then they can be miniaturized. And right now, after ATIS, we are developing for the ESA D3S mission, which is a bit larger than a CubeSat, a very wide field imager named wide field auroral imager, both in the UV and in the visible, which is an hyperspectral or a spectral imager instrument. You can see the IXO meeting presentation of Etienne Lecoeur last month, where we show that this instrument is really, really interesting and is able, if it's at 3,000 kilometers altitude, so a bit higher altitude than LEO, it is able to take pictures of the full auroral oval. So it means that we are able to see the full oval in one picture, and then, of course, to reconstruct the full precipitation of the instrument in one picture. And that is very interesting because for each point of the image, we have a spectra with almost the same, let's say, almost the same spectral resolution as that is, let's say, 1 nanometer. So, yes, this is very important point. So to conclude and give you some, let's say, a more larger overview of what we are doing at the Grenoble Space Center, I give you some short highlight of the other project we are developing in Grenoble, other payloads. So we are developing, for example, NanoBob. NanoBob is a quantum communication space demonstrator in an uplink configuration, and we aim to launch it in 2025. We also have a cubesat, which is an imager with a quite high ground-based resolution of 10 meters. And the idea is to have onboard the satellite a dedicated artificial intelligence software to allow to do some interpretation of the picture. And our first use case is to see if we are able to detect some deforestation in some dedicated part of the world, in South America or in Africa, or on some island in Papua. So the idea is to do this, and we aim to launch it at the end of 2022, perhaps just beginning of 2023. We will, in 1 month, launch SingSat, which is a LoRa IoT demonstration, and it is an hosted payload on board a satellite developed by a Polish society, Sat Revolution, named Stork. And yeah, it will be launched at the end of June this year. And we also have the nanocarb collaboration dedicated to the greenhouse gases monitoring. And we did this year an airborne test of this, and the results are very, very interesting. So this gives you an overview of all the projects we are developing at the CESUG. And of course, do not hesitate to contact us, and we will be very glad to collaborate on payloads on satellite or satellite missions for this. So thank you for your attention, and do not hesitate to ask me some question if you have some.
Okay, thank you very much, Mathieu. It seems like you have a lot of projects upcoming on your shelf, and it's very impressive what you've been able to accomplish with AMCA Set. So we'll open it up for questions. If you have any questions, please feel free to raise your hand by clicking the raise hand button on the lower right-hand side, or feel free to type your question in the chat. So it seems like you've done a lot of very impressive work on optical instruments over at Grenoble. And I was wondering, optical instruments are definitely quite valuable, but one of the challenges, for example, is data volume and also calibration, as you mentioned. I was wondering, what would you say were some of the biggest technical difficulties for you in developing AMCA Set and the optical payloads?
That's a very interesting question. For AMCA Set, one of the problems is that we did not find some objectives that fit with our requirements. So we had to design a new objective, and it has been quite difficult. But and the most difficult was to find a company able to realize this objective. For some other optical payload, the difficulties, especially for spectrometers, are the thermal problems. Of course, in optics, temperature gradient can be very, very critical, especially when you are doing some interferometry. And we had some very strong, let's say, system difficulties to keep the gradient at very low levels. So that is quite difficult. We are dealing on passive cooling, and we are also thinking with some companies near Grenoble to include some active cooling in some CubeSat, and this is a challenge because of course the consumption is then very important. We try to reduce it, but could be very important. Another point in optic is that of course you need to point quite precise area, and then the ADCS of the satellites need to be quite precise. And as I mentioned in AMCA Set, the ADCS has a failure, and it causes us a lot of difficulties because, of course, we need to wait the good orientation using the rotation of the satellite. So optics is feasible, but it is quite demanding for the satellite, especially in terms of ADCS and in terms of thermal studies.
Okay, thank you very much. So in your mind, so here in Taiwan, we have a lot of experience with in situ plasma sensors and GPS radio occultation, not so much optical. Do you have any ideas about how the optical observations might be complemented by in situ or, for example, ionospheric profiles measured using radio occultation?
Oh yeah, of course. In fact, with the code that we have developed, transsolo, we also are able to reconstruct all the electron flux and then the electron profile into the ionosphere. So of course, this can be complemented with, let's say, GPS radio occultation or some other data. You can have from the ground with ionosonts or some other. Yeah, so definitely this can be complementary, and this can help a lot. Let's say that space weather is really a system science with a lot of different instruments from the ground and from space. And of course, the more instruments you have and the more data you can cross, the more precise the reconstruction of the ionosphere states and dynamics will be. So definitely, yes, it's very, very important to cross the data of the optical instrument with some other. On ATIS, we will cross with a particle spectrometer built by some Russian colleagues. Because, of course, as it has been done on the Reimei Japanese satellite, it will be very interesting to have at the same time the aurora and the particle fluxes coming into the satellite, so coming into the atmosphere if you are in LEO. So yes, definitely there are some very interesting challenge to cross, let's say, plasma data with optical data.
Okay. Thank you very much. And you mentioned that you partnered with industry in the development of AMCA Set and ATIS. I was wondering. Oh, I'm sorry.
Oh, Lauren. Yeah, there was a cut for a few seconds.
Oh, yeah. I'm sorry. Can you hear me now?
Yeah.
Okay.
Yeah, it's good.
Yeah. So you mentioned that the spacecraft was developed in partnership with local industry as well as the payload. I was wondering. So how much of these tasks did you handle in-house at the university, and how much did you work together with private industry on, and what was sort of the strategy behind that breakdown?
In fact, yes, that's very important. We let's say developed a quite original way to collaborate with industry. So we use some components of our partner industry. For example, Teledyne E2V give us some detector or some processor for for the project. But we also do some, let's say, skills sponsorships, meaning that the industry sent to us some of them engineer and try to learn us their skills in space industry. And there is very strong, close collaboration in this. What is very, very interesting is that, of course, for some projects, we are working with students. So the engineers in the industry can learn to the student what is the space specificity. And for example, for thermal simulation, we work a lot with Air Liquide. So there is a very close collaboration. We try to work together to develop the project, and of course the industry also help us to fund the project. So yes, this is through. It can be sponsorship. It can also be research contract. So we try to do it and to have a very, very close collaboration like this, and to invent some new way to collaborate. And that's very, very interesting.
Okay. So out of curiosity, what sort of tasks would you hand to a student as opposed to a professional engineer? And would the student be directly supervised by a professional engineer? Was there some type of management mechanism?
Yeah. In fact, we have some project with some students and some other with very few students. So there are two kind of projects. Of course, when we are working with ESA, for example, with very strict deadline, it's difficult to have a lot of students. But for some other project, it can be design of the objective of AMCA Set, for example, have been designed by students in an optical engineering school, helped by some professional engineers. So there is a very strong, let's say, supervising of the student. But this supervising can be done by academics, but also by engineer from company, and that is very original and very interesting, because for the company it gives them access to motivated student, and they can hire him after their intern or their project. And for the engineering company, they told me that they learn a lot from the student and from the other engineers. So it is a win-win collaboration, definitely.
Okay, thank you very much. I think there's quite a few good lessons learned there that we can probably consider for our own projects. We have a question typed in from Christian. Question is, you did mention on several occasions your mission length and possible extensions. How does that compare to your subsystem design lifetime? Did you design your system for some ideal lifetime that you would like to achieve beyond your extensions? I assume you were, of course, not shooting for the low end, i.e., your minimum required mission duration according to your funding and mission requirements. So I am curious what you would ideally like to see: 2 years, 3 years, 5 years, or longer?
That's a very good question. In fact, we are using COTS, mainly COTS, but there are different levels of quality for COTS, and we are trying to calculate, let's say, the amount of radiation that will be received by our electronics in the satellite. So this is one point. Of course, we also have the operation of a satellite cost a bit. So the duration of the mission is also driven by the cost of the operation. Then, what is the ideal duration for a CubeSat mission? That's very challenging, because it depends on the mission. It depends also on the size of the satellite. For a 12U, considering the cost of the satellite, the cost of the launch, we think that it's a bit short to have only a 1-year mission. So we try to put in a 12U satellite some more, let's say, a hardened component to allow a longer mission. Of course, the extension is also driven by the cost of the operation and by the life of the satellite, to see if the satellite is still working or not after the nominal mission. So this is a kind of trade-off about that. One very interesting thing is that since we are using COTS, we are trying to make some protection, for example, to avoid some latch-up destruction of the system. We put on all EPS in the satellite some current limitators to avoid that the latch-up destroy physically the components. So we try to build an environment which allows these COTS to have a longer duration in orbit. But this is true for LEO, where the radiation are not too strong. Of course, if we want to go further, especially in the radiation belt, of course, we will need some stronger component, and the duration will be affected by this. This is something important. And from the beginning of the mission design, we deal with all this trade-off. We also can shield, for example, the payload. You perhaps saw that the AMCA Set payload have been shielded by 3 millimeters of aluminum to diminish the total ionization dose received by the components. So it's really a trade-off. And let's say that the larger the satellite is, the longer we try the longer mission we try to have, because of course there is a cost trade-off for this.
Okay, thank you very much. I hope that answers your question, Christian. So with all your upcoming missions, sort of what is the manpower you have at your center?
In fact, the Space Center is, let's say, a federation of laboratories. So there are some, let's say, coordination manpower. So we are 15 people, mainly some system engineer or project manager, and then we use the technical skills in the different laboratory of the Grenoble area and in the companies. So it's the core of the CESUG is something like 15 people, and then we work with the different laboratories and company to increase our strengths. And there are more than 100 laboratories in Grenoble, so the area is really rich for this skills. I thought that Christian asked another question. Our objectives really depend of the possibility. The best, of course, is for space weather is to be able to have one entire solar cycle, but it means 11 years, which is very long for CubeSats. So for ATIS, let's say that the conservative hypothesis is 2 years, because we don't know if we can keep it longer, but we would like to have 5 years because it's a alpha cycle and it gives us some very interesting information for space weather to have at least alpha cycle. So the objective is really to reach alpha cycle for space weather monitoring.
Okay, thank you very much. And yes, as we noticed in the case of our own spacecraft, we did notice a lot more single event effects than we were expecting, which again is a pretty important lesson learned.
Yeah, one problem is that we have a lot of reboot and unwanted reboot when the activity is higher and after quite a long time. So there are some strategy. I'm not a software guy, but there are some strategy to avoid to have some robust software and avoid too strong reboot in the satellite.
Yeah, in our case, our most critical anomaly was basically in our main power bus. Our reset circuit has a CMOS inverter, which has no latch-up protection. And basically, when that latches up, the spacecraft will essentially hang until the battery discharges to a significant enough level. So that means basically the way we view it is our spacecraft, that portion of the spacecraft is somewhat radiation sensitive, and basically if it gets hit there by an energetic particle, then the spacecraft goes into a coma for several weeks.
Yeah, that's a problem. This is something we took into account, and yes, we set some, let's say, anti-latch-up which are currently mitigating just after the EPS. But on CMOS, it can be a difficulty because there are some, it can introduce some delay, and then it can perturb the, let's say, turn on sequence of the CMOS. So you have to take care about that also.
Yep, that is a lesson learned for us, and it's definitely something we're implementing on future revisions.
Yeah.
So are there any plans based on your first results on AMCA Set to fly the payloads again on perhaps a smaller CubeSat, or will you be moving straight on to the 12U?
In fact, the payload of AMCA Set will fly on ATIS as a secondary payload. Then for next step, there is no plan, but of course, if some partners wants to fly AMCA Set, we'll be very glad to share our experience on this. So yeah, there are some collaboration possible with AMCA Set and with the payload we developed.
Okay, thank you. We'll keep that in mind. Are there any additional questions from the other participants? If you have any questions, feel free to raise your hand or type it in the chat. I think it looks like we don't have any additional questions. Okay, well, Mathieu, thank you very much for taking the time to share your experiences. all the best of luck on your future spacecraft. And hopefully when the travel restrictions are over, we can get back to traveling abroad and mutual visitations again.
Yeah, that will be with really pleasure. And yeah, I will be very glad to collaborate. So thank you for all. And yeah, talk to you soon.
Okay, talk to you soon. Thank you very much, Matthew.
Bye-bye.
Thank you to everyone for participating. Bye-bye.